Hi guys, my name is Rachel. I am starting this YouTube channel to post educational video content about the geosciences and related fields, as I have always been a fan of watching videos rather than just reading textbooks. And I noticed throughout my schooling that there are a lot of short and really informative videos out there for basic concepts regarding chemistry and biology, but not so much with geology. So that is my goal for this channel. So for this episode, we're going to be talking about the fundamental concepts in science and geology. So obviously, fundamental concepts of science and geology is a pretty broad topic, and we're not going to be covering everything, but what I want to cover is basically, first of all, how scientists think and conduct the scientific method, which, as you'll see, is more simple than you might remember from intro science courses. Also, I want to talk about fundamental concepts in geology and geology's importance. Why do we need to study geology? Why is it awesome? Because it is. And fundamental concepts that govern geologic principles like actualism, uniformitarianism. And so we'll talk about that. So first, let's discuss hypotheses, theories, and laws. In science, we develop testable hypotheses to explain phenomena that we observe. So what does that mean? When we say testable, we want to be asking questions like, how do mountains form? Or what is granite made of? Or why is this rock fine-grained, but this one's coarse-grained, and they're the same composition? Those things we can answer, but we can't ask questions that aren't testable, like what's the meaning of life? You can try and answer that, but it's probably not going to be a scientific answer that you came to from experiments and observations made from those experiments. So we try to ask questions that are testable. And these questions aren't necessarily hypotheses. We can make hypotheses from starting with a scientific question. Now, scientific theories are actually really well backed up. So theories develop when hypotheses have been supported from many observations and experiments, and basically have been put under scrutiny by many different scientists in different laboratories doing all sorts of different experiments, and it still holds up. And that's what results as a theory. Now, theories can be used in common language quite wrong. So this just a theory quote I have down here, just X that out. If you're going to do science, that is not a thing. Just a theory is not a thing. Now, laws in science are also sometimes called principles, and they explain phenomena such as gravity, or like in geology, principle of superposition, which we'll talk about in a later episode. Basically, it's just saying that if a rock layer is underneath another rock layer, then the underneath one is older. You would think that would be common sense, but you would also think that about gravity. So things like this that are so obvious and nothing can really disprove these things, these are scientific laws. With those definitions straight, let's move on to the scientific method. Now, this you've probably seen in high school science class when you had all these little bubbles and you were like, oh my God, this is so complicated. Science is so complicated. What the heck? Why are we doing this? Why? But no, it's so easy. You probably do this way more than you think. Just think about the last time that you made any kind of prediction about anything, about how good a movie was going to be, about how a plate of food was going to taste, about how cold or hot the pool was going to be when you stuck your toe in. Any prediction. If you then do the thing to test that prediction, like stick your toe in, you are then testing your hypothesis that it's going to be cold, and then you're drawing conclusions based on your observation that, dang, that is freaking cold. And that's your conclusion. And that's the scientific method. It's so everywhere that nobody realizes it. But you are doing science 100% of the time, pretty much. We all are, because science is everywhere. It's not just these abstract things that we think about are really complicated, like rocket science. It's not, a bunch of math on a blackboard. It's everywhere, and it's amazing and beautiful. It's what makes life life. It literally is. Now, geology. This is a field of science. A lot of people might just think you're a geologist, you do rocks. That's what I get all the time, and I'm sure a lot of people do. But no. So you might know there are some uses to geology and geologists and what we study. For one, energy. You probably have heard that, oil and gas That's where geologists come in. Another thing, water, hydrogeologists come in. Another thing, mineral resources, economic geologists come in. Environmental science, geologists, and a bunch of other geo-type scientists. Climate change, geologists and other geoscientists. Natural hazards, earthquakes, landslides, volcanoes, floods, geologists, seismologists, geochronologists, volcanologists, all these geoscientists. Nanotechnology, nanogeoscience. My actual doctoral advisor is a nanogeobiologist. Oceanography, this is kind of where my field of geology fits in. I am a marine biogeochemist. And alien life, astrobiology, guys. Geologists are key importance for this field as well. So all of these things are relevant in geology. And if you're a geologist, you can do any of these things you want to do. It is awesome. Geology plays a role in so many different fields of science that it's basically, it can be anything you want it to be. And that's why it's amazing. Now moving on to the fundamental concept of geology, one of the fundamental concepts of geology, I should say. This specific concept, actualism or uniformitarianism, is what we base historical geology off of. So basically, we're saying that the processes that we observe today on Earth have been happening throughout Earth's history. Now, that's not to say that things haven't changed. For example, things like atmospheric chemistry. I mean, at the beginning of Earth's life, it didn't have oxygen in the atmosphere. Plate tectonics was occurring, but a lot faster, and we'll talk about that in later episodes. But basically, the general cyclic processes that we observe on Earth today are occurring maybe at different rates, maybe at different scales, but generally the same as they have been throughout Earth's history. And that is pretty useful for geologists. Now, the last thing I want to hit in this lecture is talking about fossils. Really, this slide is meant to talk about anything in geology. If we see a bunch of rocks or fossils or whatever it may be, that represents the past in some way or past processes in some way. And so we have to determine from that what it means. What was the series of events going on there? And so I put this picture up because I like showing that, yeah, sometimes it looks like that, but most of the times it does not. We typically go up to an outcrop and we'll see something all scattered about, and we act like investigators. I don't know about you, but I love kind of forensic shows and watching them come up with the criminal because they put all these puzzle pieces together and use scientific techniques. So I like to say that geologists are like forensic investigators. We investigate the outcrops as though it's a crime scene, and then we piece back the puzzle pieces together to reconstruct the history of events, the geologic history that occurred to make that formation of rocks look like that today. That is all for today, guys. I will be coming out with a lot more content soon. I want to make this analogous to chemistry and biology crash course. I love the entire crash course series on YouTube, and I want to give the people of YouTube a GEO version of that. And I hope that this helps. So please let me know any topic suggestions you might have, any content suggestions you might have, any suggestions at all. I'm all ears, and have a nice day.